Now we've talked about an electric field, and we're now going to do some calculations around charged particles and the forces that they exert on one another. The force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Now once again, doesn't this look a heck of a lot like the gravitational formula, except that those are the masses. The K value is different to the G value, but otherwise it's a very similar proportionality. The force between the two charges is measured in newtons. Coulomb's constant is 9 times 10 to the power of 9. The minute I've got a constant, I have to use the correct units. I must use coulombs, I must use newtons, and I must use meters. The charges must be measured in coulombs, and the distance between their centers must be given in meters or calculated into meters. So if I've got 2 point charges and they are placed 30 millimeters apart, the one that carries a charge of -6 and the other one positive 9. What is the electrostatic force between them? So F is equal to K Q1 Q2 over R squared. And I substitute in the values, it's 9 times 10 to the 9. The first charge is 6 nanocoulombs. So I am going to need to make that into a coulomb. And how do I do that? Nano is times 10 to the 9. So it's times 6 times 10 to the 9, -9, sorry, nano is -9, times 9 times 10 to the -9 again. And then I am going to take the distance between them, which is 30 millimeters, which is 0,03 meters, and don't forget to square it. So there's a lot of unit converting going on in there. And when I punch all of that into my calculator, I land up with 5,4 times 10 to the -4 newtons. My answer will come out in newtons. And that is going to be, I have got a negative and I have got a positive, which means that that is going to be an attractive force. Attraction, attractive, something like that. What would happen if the two charges touched each other and separated? What charge would be on each sphere? The way I do that is I say charges always like to even out their charges. So if they were to touch each other, it would be -6 plus 9, which would equal +3. That's the overall charge, because they would do that, and then it would divide between the two charges. So you would land up with 1,5 times 10 to the -9 coulombs each. So what about if we have these ones? Press pause and try and work through the problems, and then we'll look at the answers. Again, I've got two charges, so its force is equal to K Q1 Q2, and there's a distance between them. So, distance is R squared. So substitute that in, and I get 9 times 10 to the 9 times 3 times 10 to the -9, because I've got to change nano. 5 times 10 to the -9, because I have to change nano. 25 millimeters apart, 0,025 squared, and you land up with 2,16 times 10 to the -4 newtons, and because they are both positive, it is a repulsive force. What if they touched each other? You would have +3 plus 5, that would mean that you would have +8 divided between the two charges, and it would be +4 each, +4 nanocoulombs each. If the charged objects touch each other, they will transfer charges until they are eventually shared out evenly. And that is something which we have done in the last two problems, even though we hadn't put that slide in yet.